Hello everyone, my name is Mahipanti and from Central Engineering College, Artificial Intelligence and Machine Learning Department, and I'm here to talk about my mini project that I've done, which is biometric spoof detection with PQC integration. So this is our agenda, what we'll be doing. So biometric authentication systems are used in long range, widely adopted for secure identification. They face two main problems: spoofing attacks and emerging quantum computing risks. So, what is spoofing attacks? Spoofing attacks includes deepfakes and physical forgeries, which can deceive sensors into accepting fake identities. This project integrates deep learning based presentation attack detection with post quantum cryptography using MLKEM for end to end security. So, this will be a problem. Biometric spoofing attacks. Modern spoofing techniques such as deepfake driven presentation attacks, generated using advanced GAN models. Deepfakes make it hard for older detection systems to distinguish real versus fake. Quantum vulnerability and lack of integration. So, as we know, quantum computers are very complex and advanced, so they can easily break through most of the authentication systems. So, that's why we need this specific biometric spoofing technique using PQC integration. So, what does this project have? What is its scope? So, we have developed a dual layered biometric system framework which has a deep learning based presentation attack detection and lattice based post quantum cryptography. This ensures real time liveness detection using a hybrid CNN model that can distinguish live samples from deepfakes or forgeries. So the MLKM is used to secure all the templates for encryption, ensuring quantum resilient storage and transmission of sensitive user data. This provides end-to-end protection, covering every stage from biometric capture to secure matching and verification within the encrypted domain. So the methodology. The research follows a three-phase methodology that blends theoretical analysis, simulation, and quantum resilient system design. So, our key focus areas will include obviously the presentation attack detection using hybrid CNN models, quantum resistant protection using lattice based post quantum cryptography, evaluation through benchmarking, threat modeling, and framework validation. So, phase one, threat modeling and quantum era. So, we identify potential biometric attack vectors that may exploit quantum advancements, study deepfake generation pipelines, and simulate quantum aided GNs. We formulate adversarial scenarios to assess the robustness of detection models. Phase 2, simulation and benchmarking. We developed a baseline deepfake and spoofing datasets using classical GANs and diffusion models. So we trained and evaluated CNN based detectors using cues such as textures, irregularities, lighting inconsistencies, and motion artifacts. We integrated quantum inspired algorithms via frameworks such as Qiskit or Penny to simulate hybrid quantum classical acceleration. We also analyzed detection accuracy, latency, and computational feasibility for real time authentication. What is the quantum resilient framework design? So basically, we combine the PAD and the PQC security model into a unified architecture for quantum secure biometric authentication. We used MLKM for biometric template encryptions, providing protection against the quantum decryption. We employed QKD for secure transmission between capture and verification modules and integrated cancelable biometrics, applying non invertible transformations before encryption to preserve privacy. So validation process. So what kind of validation process did we use? So we basically tested the framework using CNN and PQC integration under various attack intensity. So we tested this model through various attacks with various pressures and mixes and ratios. With after doing all this, we measure the accuracy, precision, recall, and F1 score, and we have got pretty good results. So this is the architecture diagram, such flow diagram. So the step one, as we know, biometric capture and PAD. The step two will be to secure feature extraction. The step three is post quantum encryption, and the step four is secure transmission and matching. So this will be our dual layered biometric architecture. So first we get the biometric input, then we perform the PAD and generate cancelable template. We encrypt the template uncerted using PQC, store slash retrieve encrypted template, and we after doing all this we authenticate the user. So this is the explanation of the previous two diagrams, and this is a sequence diagram. As we can see here, the user sends the input, gets the input, goes back. So the user sends the input to the biometric module. It goes to the PAD model feature extractor, then the PQC encryptor, and then the template database analyzes this and matches the password to the user and sends the login access back to the user. So these are the algorithms that we have used in this hybrid convolutional neural networks, cancelable biometrics transformation, MLKEM, and quantum key distribution layer. So, what kind of hardware and software have we used? So, for the biometric sensor, we use a camera. We enabled GPU enabled system. We used GPU enabled systems with NVIDIA T4 RTX. We had a secure storage server and optional, and it was optional, but we used KQD support. The software used was Python, TensorFlow slash PyTorch, and Google Colab, MLKAM, OpenCV, Qiskit, OpenElane, and we use Google Colab. So this is our code, a basic ML model where this is the PADE model where we use convolutional neural networks and max pooling for it. We also use the cross entropy loss and the optimizer Adam. So this was our output. The final output was the accuracy was 97.64% and the precision was 95.48%. The recall was 99.98% and the F1 score was 97.68%. In PQC pipeline metrics, the accuracy was 97.56% and the average latency was 2.54 millisecond. So this was our actual output of the training dataset. So here, if it is a registration for the user, then it will ask for the user's registration number, password, and if it has passed after analyzing from the template, then it will give access. If not, it will just show invalid login. The same for user login, the same for image upload, prediction result display, and view prediction history. So these are the test cases. So, in conclusion, we developed a secure image processing system by combining presentation attack detection model with post quantum cryptography. Our results show that the PAD model accurately identifies real and spoof images while AES encryption and Kyber based key exchange protect the data during processing. Even with added security, the system remains fast and reliable, giving users accurate results instantly, making the approach suitable for future secure authentication and AI based application. So, how can we improve this in the future? In the future, the system can be improved by using real face datasets instead of CFAR10 to achieve more accurate spoof detection. More advanced deep learning models such as vision transformers or lightweight mobile networks can be added for faster and better performance. The PQC can be extended using full Kyber implementation to achieve post-quantum security. The pipeline can also be deployed on cloud platforms to test scalability and real-time performance. Finally, a user interface can be added so the system can be used easily in real authentication environments.